Welcome everyone. In this video, I'll walk you through how to train YOLO26 for both object detection and segmentation step by step. YOLO, short for You Only Look Once, is one of the most influential real-time object detection frameworks in computer vision. Starting from YOLO v1, which introduced single-stage detection, the YOLO family has continuously evolved through improvements in accuracy, speed, multi-scale detection, and architectural efficiency. Over the years, advancements driven by the research and open source community, especially Ultralytics, have led to modern versions like YOLO26, which support detection, segmentation, and deployment on edge and cloud platforms. Let's get started. For this tutorial, I'll be using my own custom labeled dataset focused on tree trunk and branch detection. The dataset contains a total of 859 images, with 687 images for training, 80 for validation, and 86 for testing. All images were carefully labeled in RoboFlow, where we annotated tree trunks and branches. RoboFlow allows exporting labels in multiple formats, and for this project, we exported everything in YOLO26 format and downloaded the dataset as a zip folder for training. In this first cell, we prepare a clean and stable Python environment before training YOLO26. This step is very important because deep learning frameworks are sensitive to library version mismatches. First, we uninstall NumPy using pip uninstall numpy. This removes any existing NumPy version that might conflict with other libraries. The -y flag automatically confirms the uninstall, and -q runs the command quietly. Next, we install a fixed NumPy version, specifically version 1.24.3. Fixing the NumPy version ensures compatibility with SciPy, PyTorch, and the Ultralytics framework. Newer NumPy versions sometimes break older dependencies. Then we install SciPy version 1.10.1, which is commonly used for numerical operations, optimization, and scientific computing. This version works reliably with the chosen NumPy version. After that, we install or upgrade Ultralytics, which provides the YOLO26 training, validation, and inference pipeline. The upgrade flag ensures we get the latest stable release. Finally, we verify the installations. We import system utilities and print the installed versions of NumPy and SciPy using small Python commands. This confirmation step helps us ensure that the environment is correctly set up before moving forward with dataset loading and model training. In this first cell, we fix NumPy-related version conflicts, which are very common when working with deep learning libraries such as YOLO26. This cell must be run first to ensure a stable environment. We begin by importing system-level utilities like sys, subprocess, and importlib, which help Python manage installed packages. The printed lines with equal signs are simply for clear visual separation, so users can easily follow what the cell is doing. Next, we check the currently installed NumPy version. This helps us confirm whether NumPy is present and identify potential incompatibilities. If NumPy cannot be imported, the script safely reports that instead of crashing. We then uninstall NumPy, SciPy, and Matplotlib. These libraries are closely linked, and mismatched versions often cause runtime errors. Removing them together ensures a clean reinstall. After that, we install compatible and stable versions. We restrict NumPy to versions lower than 2, SciPy to versions lower than 1.11, and Matplotlib to versions lower than 3.7. These ranges are well tested with Ultralytics, YOLO, and PyTorch. Finally, we verify the installations by printing the installed versions. The last section clearly reminds you to restart the kernel, which is mandatory for the changes to take effect before continuing to the next cell. This cell demonstrates a simple, robust, and GPU-aware training workflow for YOLO26 using the Ultralytics framework. The goal here is to show a clean training setup that works reliably on both GPU and CPU, while minimizing configuration conflicts that often confuse beginners. We begin by importing essential libraries. The OS module is used for file and directory handling. Torch provides access to PyTorch utilities such as GPU management, and YOLO from Ultralytics is the core interface for loading and training YOLO26 models. The printed separator lines are purely for readability. They help clearly mark the start of the training process in the console output, which is useful when training runs for a long time. Next, the script checks whether a GPU is available. If CUDA is detected, the GPU cache is cleared using torch.cuda.empty_cache. This step helps prevent out-of-memory errors caused by leftover tensors from previous runs, especially when experimenting with different batch sizes or models. The code then confirms that the dataset configuration file exists. While we do not focus heavily on paths here, this check is critical. It prevents silent failures by immediately notifying the user if the dataset cannot be found, and even lists nearby files to assist debugging. After that, the training device is selected. If a GPU is available, the script automatically assigns training to the first GPU. Otherwise, it gracefully falls back to CPU execution. This makes the code portable across systems with different hardware setups. The model is then loaded using YOLO, YOLO26n-seg.pt. This line automatically downloads the YOLO26 nano segmentation model if it is not already present. The nano variant is intentionally chosen because it is lightweight, fast to train, and ideal for testing new datasets or debugging pipelines before scaling up to larger models. Training begins with a minimal and stable set of parameters. The number of epochs defines how many times the model sees the entire dataset. The image size controls the input resolution, balancing accuracy and speed. The batch size determines how many images are processed simultaneously and is kept small to avoid memory issues. The device parameter is crucial because it explicitly tells YOLO whether to use GPU or CPU. Additional parameters such as workers are kept low to reduce multiprocessing related errors, especially on systems with limited resources. Validation is enabled so the model is evaluated during training, and checkpoints are saved for later analysis. Finally, the entire training process is wrapped in a try except block. If any GPU-related error occurs, the script automatically retries training on the CPU. This fallback mechanism ensures that training can still proceed, making the workflow reliable, beginner-friendly, and suitable for real-world experimentation with YOLO26. After completing 100 epochs, training finished in approximately 1.338 hours. The best and last YOLO 26 segmentation models were saved successfully. Validation on the test set shows strong performance with trunk detection outperforming branches in both bounding box and segmentation metrics. Inference is very fast, taking only a few milliseconds per image, and all results are saved to the experiment directory. These are real tree images, and the YOLO26 segmentation results you see on the screen clearly demonstrate how the model identifies trunks and branches in practical scenarios. Thank you so much for watching this tutorial. We have included the complete training code and step-by-step instructions for training YOLO26 in the video description, so please be sure to check it out. And don't forget to subscribe to our channel. This is our very first video, and your support truly means a lot to us.